All right, so starting out looking at this, what do we see, what do we notice? So in our product, we have an alcohol and a ketone. In our starting material, we have an ester and a ketone. And what you notice in the product is that the ketone is still there and the ester is gone. So that should tell you something. But it should also make you think, wait a second, esters are less reactive than ketones, right? Because esters can do resonance. That makes their carbon of the carbonyl, carbon 4, less reactive. So I need to do something to this ketone to not let it react. And that's when we think about our mass, the protecting group, the acetals. So if we take one step back, what would this have been? Well, let's see. I can't do any chemistry on this unless this is protected, right? Because a ketone is more reactive than an ester. I have to mask the ketone. And the thing you learn about protecting groups is they go on first and they come off last, right? Because if you're protecting something, you need to protect it from the start to the very end. So one step back, I would guess we had something like this. Now, how did I know that? And how do I know it's this? I don't. I just use any protecting group I want to. Any sort of like mask type thing is acetal. Because I know this way carbon 2 isn't as reactive as it would be if it was a ketone, right? This makes it less reactive. That allows me to do chemistry on this. Now, a thing to think about, the next step back, how do I turn an ester into an alcohol? How can I do that? Well, what's going on here? Let's look at carbon 4. What does carbon 4 have on it? Here it has 2 H's. And here it has how many H's? Zippo. What kind of reaction do I need to do? I need to do a reduction. How many ways do you know how to do reductions? Well, you know diol H, sodium borohydride, and lithium aluminum hydride. Well, hopefully you remember diol H, of course, reacts with esters, but what does it turn esters into? It turns it into an aldehyde. Is this an aldehyde? No. Okay, so not diol. So now you're stuck with sodium borohydride and lithium aluminum hydride. What do you know about the differences between those two things? Well, boron is where on the periodic table? Above aluminum, I just looked, right? And aluminum is farther down. So aluminum, as you go down the periodic table, what happens? You get larger. So the hydrogens on aluminum have less orbital overlap, so they're actually more reactive. Remember, sodium borohydride, because it's not as reactive, it only reacts with aldehydes and ketones. Lithium aluminum hydride reacts with aldehydes, ketones, esters, and amides, and even carboxylic acids. So in this case, you're going to need to use that more reactive reagent, lithium aluminum hydride, to get to all the way back, and this actually goes all the way here then. And I actually spoke too soon. You do need to go one step back because you need to put the protecting group on. Duh. So one step back, sorry, forget. I was just excited. One step back. Will be this ester. And I would argue they should have shown this piece in there too, right? To, be fair. There's another alcohol produced. Now this one step back, there you go. So what we need for reagents now, let's do forward direction. So the forward direction, the first thing we need to do is put on the mask. And we need H plus catalyst to do that. Again, this will react with the ketone first because the ketone is more reactive. Puts the mask on. Now we need to add the H's to this ester. How are we going to do that? We're going to do that with lithium aluminum hydride. Step 1. Step 2, water or H+. And then when we want to take the mask off, we add H plus and water. Right? Or maybe you could combine this step and this step to take everything off at once. All right. So now with this one, should tip off some sirens or buzzers in your head and think a little bit, wait a second. I have a alcohol, a tertiary alcohol, and a ketone. Again, you only know so many ways to make tertiary alcohols, and usually the ways you make these things are with Grignards. And you also know Grignards react with ketones. So this is going to be one of those ones, again, where we need to use that protecting group, that mask, for this. Also, they show you the starting material. So I've numbered the product. That's easy enough to number, right? Now, how do I go about numbering this? So when in doubt, what I always like to think about doing is I try to go the easiest way possible, right? And if they're showing me this, where there's all of a sudden carbon 4 has a bromine on it, right? And carbon 4 here, right, looks like it's attached to carbon 1 that has the oxygen on it. Right? What does that make me think of again? Well, wait a second. Carbon 1's electrophilic. Carbon 4 would have to be the nucleophile, right? If I break this carbon 1, carbon 4 bond, that makes me think carbonyl and Grignard. Now, looking at carbon 4 right now, I say, well, wait a second. Carbon 4 is a electrophile, right? But can I turn that into a nucleophile? Right? Can I turn this into a Grignard? I can. But here's the problem. If I make this a Grignard, will that work? Because it won't, because Grignards are going to react with ketones. So I'm going to need to do something with this ketone. I need to protect it. And so if you think you're going to use a protecting group, what do we know about protecting groups? They're the first thing that comes on and the last thing that comes off. So the first step back would be everything the same except I have a protecting group on my ketone. Now, I keep using this one version, and I'm just using it for simplicity's sake. I think it's kind of a classic one people use, this kind of thing. But it doesn't matter what, as long as it's this kind of like double dial, like a dial, it works. All right, so now I've protected that. So now I can go back to doing what we did in those first couple of problems, where I look at, okay, there's carbon 1. Carbon 1's bond to the oxygen, right? That's the carbon that's electrophilic. Let's think about breaking this bond into a carbonyl and a ketone. And how do I decide this bond? Well, because I look back and say, well, carbon 4 here must be the nucleophile because I'm going to turn that into a Grignard. So another step back, I would have this ketone, 1, 2, 3, and I would have this Grignard, right? Move these down a little bit. Number those atoms. 7, 6, 5, 4. Right? Good. That would get me to this alcohol. But I need to turn this into a Grignard first. So another step back would be and what do we know about protecting groups? Again, first to go on, last to come off. So I have to put the protecting group on first before I can do anything else. And that gets me there. So now the forward direction, I would need H plus in the alcohol. The next step, I would need magnesium in ether. Right, turns into the Grignard. Then I, of course, would add the acetone to that. And then step 2 would be adding H plus to protonate it. And then in this same step, I could actually do, right, H plus in water. Would also protonate this alcohol, but also take off the mask, the protecting group, and get us back here. And we'd also have the alcohol from before, now off the molecule. Okay, so a long, complicated problem with lots of steps, and they're asking for reagents, intermediate products, and so a lot of working backwards, looking forwards, and those kind of things. So a lot of ways you can start this problem. I'll start at the end. At least go back one step, then maybe we'll bounce around a little bit. There's lots of ways you could do this. First thing, number those atoms. Right? 1, 2, 3, 4, 5, 6, 7. 7. So let's take a look. Is that right? 1, 2, 3, 4, 5, 6. I added a carbon. Step 1 of doing problems, make sure you write them down correctly. Let's just stop that. Actually, this is okay. Number the atoms. Very good. And this would be number 8. So what you need to notice here is this is ozonolysis. So that should key to your head. What does ozone do? Ozone takes alkenes and clips them in 2, right? It makes 2 carbonyls. And if you look here, we have 2 carbonyls. So if you looked at this, you should say carbon 2 and carbon 7 actually were bonded before. And they make a 1, 2, 3, 4, 5, 6-membered ring. All right, so what is this product right here? It's a 6-membered ring. Move up a little bit. And this is why numbering your atoms is so important. Because it's easy to get lost along the way. I actually got myself lost. But because I numbered my atoms, I wasn't going to get lost. So 2 and 7. 7 was bonded to 6, 5, 4, and 3. Let's not forget about 1 and 8. 8 and 1. Very good. So now maybe I look at this. This at least give me one step back. And now I look at this and maybe I'm confused. I don't know exactly what to do here. So let's skip back up. Maybe we can answer some of these ones along the way. And that'll help us know what's going on here. So, in this first one, what's happening? We're taking an alcohol and we're turning it into a ketone. So we have a hydrogen here and we don't have a hydrogen here. So we're taking away hydrogens. If we're making more bonds to oxygen, that's an oxidation. And you know a couple ways to do this. You know PCC and chromium. It doesn't matter what, either one works fine here. Right? So I think in this one they wanted you to use chromium. Cool. Okay. All of a sudden from here to here, what happened? Well, we added a carbon. Right? How do we know how to add carbons? And it's just a CH3. It's not a nitrile. Right? We're not adding that. So it's just really all we need is a Grignard. And the most simple Grignard we can have is a methyl Grignard. Right? So that adds 1 carbon. So that was step 1. And step 2 will be H+. Good. If we add concentrated sulfuric acid to this, what's going to happen? We're going to protonate the alcohol. We're going to activate it. But there's no good nucleophiles around. So what happens if we have an activated alcohol with no good nucleophiles? We do a E1 or E2. So we actually make an alkene here. So this would be what we made. So now it looks like they want us to do like a rigmarole here. If I say 1 and 2, 1 and 2, they want me to put an OH on the less substituted carbon of the alkene. Who remembers how to do that? BH3. Remember BH3? Old school. Right? BH3, H2O2. Yay. Right? The anti-Markovnikov way to add alcohols to less substituted carbon. So now we put the carbon or the oxygen on 2, right? We see if we've moved this around. And now we turn it back into a ketone. So we're going to do, what are we going to do again? Chromium. That oxidizes it. And now they're telling us, oh, now we want you to make another alkene. So what do you think we need to do? Again, we're going to do a Oh, let me check. What else have we added? Be careful. Let's number some atoms here where we're at. Because if we've noticed, some of you maybe have 1, 2, 3, 4, 5, 6, 7. What are we missing? We are missing carbon 8. So we need to add that carbon. How are we going to add that carbon? Methyl Grignard again. So CH3, MgBr, step 1, step 2, H+. That gets us to this. And if we take this and treat it with concentrated H2SO4, what happens? We make an alkene. Why do we make the alkene there? What's the rule? Zaitsev's rule, right? We make the most substituted alkene because that's the most stable. The more substituted you are, the more stable your alkene. So we do an E2 or E1, probably an E1 elimination. Get to this alkene, and then to double check our answer, if we cut it here, we'd get this diketone for the product from ozonolysis.